Alright, now let's move on to chapter 5, simple mixtures. Up to now, up to chapter 4, we mostly dealt only with pure substances. And from chapter 5, we'll consider mixtures, a bit more complicated system. So we'll first deal with simple mixtures, simply mixing different kinds of materials and they are non-reacting to each other. So simply mixed ones, such as air, right? And if there are too many substances mixed together, it's too complicated. So we'll first consider mixture of two different materials, right? Okay. So we'll first describe thermodynamics of mixture, such as enthalpy, entropy, Gibbs free energy, etc., how they are different from those of pure substances. And especially for mixtures, there are interesting properties such as partial molar properties. Several partial molar properties are present, such as partial molar volume, partial molar Gibbs energy, etc. We will introduce the concept of partial molar quantities and the followings. Okay? And we will also consider thermodynamics of mixing. If you mix together two different substances, what would happen in terms of thermodynamics, in terms of thermodynamic variables? Okay? So we will consider this. And we will also deal with liquid finally. Okay? We almost always consider only gases, right? And we'll see the difference between gas and liquid and how we can describe the behavior of liquid using thermodynamics. Alright. Simple mixture. So in chapter 5, we'll only consider very simple mixtures, non-reacting substances, okay? And we'll only consider binary mixtures of two different substances, okay? And we'll deal with energies of the mixing process itself, what kind of thermodynamic properties, enthalpy, entropy, or Gibbs energy changes upon mixing two different non-reacting substances, okay? Alright, before we move on, if we have mixtures, we already have learned Dalton's law, right? If there are two different substances in a mixture, the summation of the mole fraction of each component, XA and XB, is equal to 1, right? And we also learned about partial pressures if these materials are gases, right? So the sum of partial pressure should be equal to total pressure. And for mixtures, there are interesting properties, including partial molar quantities. One representative example of partial molar quantities is partial molar volume. So let's see what is exactly partial molar volume. The definition of partial molar volume is described here. Partial molar volume is the contribution that one component in a mixture makes to the total volume of a sample. So, if we mix two different things, volume would increase, right? And partial molar volume is the contribution of one component. Okay? Let's see an example. Let's say that we have large amount of water, H2O. Okay? And we add 1 mole of H2O to this large amount of water. And we observe that total volume increases by 18 cubic centimeter per mole. Okay? So, molar volume of H2O is 18 cubic centimeter per mole. Okay? Very simple. Let's say another different cases. We have large amount of ethanol, ETOH. And we add same amount, 1 mole of H2O to large amount of ethanol. And we observe by experiment, volume only increases by 14 cubic centimeter per mole by adding 1 mole of H2O. Total volume increases 14 cubic centimeter, which means that partial molar volume of water in ethanol, large amount, is 14 cubic centimeter per mole. That's how we define partial molar volume, right? The reason why partial molar volume of water in different environment is different is that they have different environment. Water and ethanol have different molecular structures, right? So as liquid, they have different molecular arrangement. Okay, so as a result, they have different partial molar volume. Okay. Similarly, we can plot the partial molar volume of water or ethanol, okay, as a function of composition, right? So y-axis here on the left is partial molar volume of water, okay? Y-axis on the right is partial molar volume of ethanol, okay? And x-axis represents the composition, mole fraction of ethanol in a mixture, okay? As you recall from previous slide, when mole fraction of ethanol is 0, when there is only water, partial molar volume of water is 18 cubic centimeter per mole, right? Remember? Okay. But when mole fraction of ethanol is 1, when there is only ethanol, large amount of ethanol, partial molar volume of water is here, 14 cubic centimeters per mole. So depending on composition, partial molar volume of water or partial molar volume of ethanol changes, okay, because they have different environment. So different composition result in different molecular environment, different molecular interactions, right? Which also result in different thermodynamic properties. And we'll learn about those things, right? So formally, by experiment, we can measure partial molar volume of each of these species in a mixture. But we can also define formally partial molar volume as this formula. So partial molar volume, denoted as Vj, J is a kind of species, right, in a mixture, is defined as round V round Nj at constant pressure, temperature, and N prime, which means that partial molar volume means how total volume changes as a function of composition, as a function of total moles of species J when pressure, temperature, and other substances are constant. Okay, this is the formal definition of partial molar volume. Okay. One thing we can know from this formula, from this definition of partial molar volume, is that since volume is extensive property, number of moles are extensive property, right? So partial molar volume should be intensive property. Okay? It does not change no matter what the size of the system is, right? So partial molar volume is an intensive property. Oops. So since partial molar volume is defined as partial derivative of volume as a function of number of moles, if you have information about total volume as a function of composition or the amount of material, number of moles, then partial molar volume should be the slope at a specific position, right? Specific number of moles. Okay, simple. Okay. Then let's consider simple binary mixture. Okay. For a simple binary mixture, the composition can be changed by addition of A or B, right? If there are two different substances, A and B. So if there is change of number of materials for A, D and A, and also if there is a material change for B, D and B, then those will result in change in total volume, dV, right? And the ratio, how much total volume change as a function of number of moles of A or B, should be represented as partial molar, partial derivative of total volume as a function of number of moles, right? Which is partial molar volume, right? So dV can be represented as this, right? As we did many times in chapter 2 and 3, right? And each of these partial derivative corresponds to partial molar volume of A and partial molar volume of B. Simple, right? Okay? And if the relative compositions are constant, or if partial molar volumes are basically constant, then these can be considered as constants, and we can simply integrate both sides, right? And you can get this, right? Total volume is equal to Na times Va plus Nb times Vb. Okay? Very simple. Let's keep this slide. Okay. So other partial molar properties can also be defined similarly. Okay. So for example, partial molar Gibbs energy. We already have seen this, right? Before in chapter 3. Partial molar Gibbs energy can be defined as partial derivative of total Gibbs energy as a function of number of moles, right? And we remember that this is the definition of chemical potential, right? Chemical potential is same as molar Gibbs energy for pure substance, right? Remember? Okay. So chemical potential is defined as partial molar Gibbs energy. Okay. So for example, if you have information about total Gibbs energy as a function of composition, as a function of the amount of materials, the slope corresponds to chemical potential. Okay? And similarly to the derivation that we got for partial molar volume, we can easily obtain this expression, right? Total Gibbs energy is equal to Na mu A 더하기 plus Nb mu B, right? As we did for here, right? You can simply get this relation, total Gibbs energy and chemical potentials. Okay? Right? Alright. So here what we can find is that total Gibbs energy changes when number of materials changes, when when compositions are changed. Right? Up to chapter 4, we only considered pure substance or closed system. So we didn't really need to worry about compositions or change of the materials, change of the amount of materials, right? But here, if you change the materials A or B in a mixture, that results in change in Gibbs energy, okay? Meaning that there is another way to change the total Gibbs energy, right? So, in chapter 3, we learned fundamental equation for total Gibbs energy. dG is equal to VdP minus SdT. pressure, and temperatures were ways to change the total Gibbs energy. Right? Now we know that if you change the composition, if you change the amount of materials, that also changes total Gibbs energy. Okay? So we can get this expression. dG is equal to VdP minus SdT plus mu A dNA plus mu B dNB plus etc. If there are many different substances in a mixture. Okay? So this equation is called fundamental equation of, not classical actually, chemical thermodynamics. This is wrong. Fundamental equation of chemical thermodynamics. Okay? This is the general fundamental equation to describe the change in Gibbs energy. So from this fundamental equation for Gibbs energy, if temperature and pressure are constant, then dG is equal to mu A dNA plus mu B dNB. Okay? And you remember that Gibbs energy has two different meanings. One of them represents the spontaneous change, right? If the Gibbs energy changes is negative. The other is Gibbs energy represents the maximum non-expansion work. Okay? So dG is equal to dW E max. This equation means that by simply changing the composition, by simply changing the amount of materials in a mixture, we can do work. Right? Very interesting. Right? The representative example of this is battery. Okay? In a battery, we are not doing any expansion work. We simply do chemical reaction, right? Inside of that. There are movement of electrons, ions, etc. They change the composition, the amount of materials that generates energy, right? Electrical energy, right? Okay? More on chemical potential. So we got the fundamental equation for Gibbs energy, okay? And by using the definition of internal energy, enthalpy, Helmholtz energy, etc., okay, we can also get fundamental equation for those of them. Okay? The U, the H, or the A. Okay? For example, for the U, since Gibbs energy is defined as U plus PV minus ds, we can rearrange it as du, and you get this. The U is equal to minus PdV plus TdS plus blah blah. Okay. So for example, at constant volume and entropy, the U is equal to this. Okay? And chemical potential mu can be represented as partial derivative of internal energy as a function of number of moles at constant volume, entropy, and other materials. Okay? You can do the same thing for enthalpy and Helmholtz energy, and you get this expression. All three of them. Right? Interesting. Chemical potential. All of them are chemical potential, including this here. Chemical potential is partial derivative of all of them. Internal energy, enthalpy, Helmholtz energy, and Gibbs energy as a function of composition, as a function of number of materials. Okay, the amount of materials. That's why chemical potential is important. It represents everything. How all these four physical variables changes as a function of compositions. Okay? Gibbs-Duhem equation. remember this relation. Total Gibbs energy is Na mu A plus Nb mu B. Okay? And if you take the derivative on both sides, dg can be represented as this: mu A dNA plus mu B dNb plus Na d mu A plus Nb d mu B. You just take the derivative on both sides of all the variables. Okay? And from fundamental equation, at constant temperature and pressure, Gibbs energy G, Gibbs energy G is represented as this: mu A dNA plus mu B dNb. Right? If there are only two substances in a mixture. Okay? So dg is here. That should be same as this. Okay? Then, which means that these two terms, dA, Na d mu A plus Nb d mu B, equal 0. Right? If there are more materials, more substances in a mixture, we can write this as general equation like this, right? Sum of Nj d mu J should be equal to 0. Okay? So and this equation is called Gibbs-Duhem equation. What Gibbs-Duhem equation tells us is that, for example, for this equation, for binary mixture, if you express this equation as for d mu b is equal to minus Na over Nb d mu A. This equation shows basically the relation between mu A and mu B. If mu A increases, since there is minus sign here, d mu B, basically mu B, decreases automatically. Okay? If mu A decreases, mu B increases. Right? They are interrelated. They cannot change independently. Okay? So that's the meaning of Gibbs-Duhem equation. Chemical potentials of each substance in a mixture are interrelated. If one of them increases, the other should be decreased. Okay? Actually, we already have seen this when you saw partial molar volume of water and ethanol. Right? Partial molar volume of water, blue line. Partial molar volume of ethanol, red line. When partial molar volume of water decreases, partial molar volume of ethanol increases. Increases, decreases. Right? They are interrelated. All partial molar properties, not only chemical potential, all partial molar properties are interrelated. That is the meaning of Gibbs-Duhem equation. Okay, now let's move on to thermodynamics of mixing. So, how thermodynamic variables such as Gibbs energy, enthalpy, and entropy change upon mixing two different substances, two different non-reacting substances. Okay? So, we already have learned that total Gibbs energy can be represented as this for binary mixture, Na mu A plus Nb mu B. Okay? And we know that from previous chapters actually, at constant temperature and pressure, systems tends towards a lower Gibbs energy by spontaneous or irreversible processes. How about mixing two different gases? If we mix two different gases, would Gibbs energy decrease? Right? You can imagine it, because mixing two different gases is spontaneous process. If we mix two different gases, A and B, they will spontaneously mix together, right? So we can imagine that Gibbs free energy change upon mixing two different non-reacting gases would be negative, right? And let's check if that's true. Okay. All right. So we'll now calculate Gibbs energy change upon mixing two different gases. Okay. First, let's consider Gibbs energy before mixing. Basically, Gibbs energy at their pure values when two different gases are separated to each other. Okay. So GI means initial, Na mu A plus Nb mu B. Okay. And chemical potential can be expressed as standard pressure plus RT log P over P naught. We have learned this in chapter 3, right? So mu A can be represented as mu A naught plus RT log P over P naught. Okay. Similarly, mu B can be represented like this. Okay? And if you express Gibbs energy like this, you always see this expression, P over P naught, P over P naught. That's so bothersome, right? So from now on, we will remove this P naught, standard pressure, from the denominator, right? Although there is P naught in the denominator, such as 1 bar, right? To simplify the expression, mathematical expression, we'll ignore this part and we'll not write this part from now on. Okay? So we'll express GI as this. Okay? There is P naught here. We just ignore them. Okay? This is the Gibbs energy before mixing two different gases. Okay? How about after mixing? After mixing, all the expressions are same, okay? Except that now initial pressure species A and B had pressure of P. After we mix two different gases together, total pressure would be P, but partial pressure of each species A and B would be PA and PB, right? So we now need to replace P by PA and PB to express final Gibbs free energy. Okay? So Gibbs energy of mixing, the difference between GI and GF, okay, should be, if you rearrange it, you can simply get this expression. Okay? Gibbs energy of mixing is NART log PA over P plus NBRT NA PB over P. Right? Which can easily be rearranged as this. First, PA over P is XA, right? Mole fraction of A in a mixture. PB over P is XB. Okay? And if you put N here, N, and you get NA over N, which is also XA, right? NA over NB over B, N is XB. So you get Gibbs energy mixing as nRT XA ln XA plus XB ln XB. Okay? And we know that XA and XB is a number between 0 and 1. Then log XA and log XB is negative. Right? So Gibbs energy of mixing is negative. Mixing two different gases is a spontaneous process. Okay? So we show that it is negative. Here is another example. Okay? Two containers of equal volume are partitioned from one another, with one containing 3 mole of H2, the other 1 mole of N2 at 25 degrees C. Calculate the Gibbs energy of mixing when the partition is removed. Okay? For both gases, it has different number of moles, but same temperature and same volume, which means that if they are both perfect gas, their pressures are different. If the pressure of nitrogen is P, then pressure of hydrogen should be 3P, right? In this example, pressure of A and B was same, but in this case they are different. So we cannot really use previous equation, this equation directly, because this equation was for two different gases with same initial pressure. So instead, we need to calculate initial Gibbs energy and final Gibbs energy separately. The equations are basically same, so we can use same expression to calculate initial Gibbs energy and final Gibbs energy, and you check the difference between them, and Gibbs energy mixing is negative, right? One thing to note from this example is that you should not interpret that this negative Gibbs energy mixing as a sign of spontaneous process, because spontaneous process for negative Gibbs energy is when temperature and pressure are constant. Okay? But here, pressures were different. So although Gibbs energy of mixing is negative, and also this process is spontaneous itself, but that does not mean that this negative Gibbs energy mixing automatically represents the spontaneous process. Okay? So now we calculated Gibbs energy of mixing. We can easily calculate Gibbs energy of entropy, entropy of mixing, right? By taking partial derivative of Gibbs energy as a function of temperature. Okay, so we can calculate it, and entropy of mixing is minus NR XA at XA plus XB at XB. Since these log values are negative, there is minus sign, so entropy of mixing is positive, right? So by mixing two different gases, we increase the entropy. We increase the randomness or disorderliness. That's obvious, right? And we can also calculate enthalpy of mixing, right? Delta G is at delta H minus TdS, T delta S. So if you calculate it, enthalpy of mixing is 0. There's no enthalpy change upon mixing two different non-reacting gases. So basically, this mixing two different gases is spontaneous process, and the driving force to make this process spontaneous is entropy change, entropy increase. Right? Okay. Increase of entropy of the system. Alright. Chemical potentials of liquid. Now we are moving on to liquid. So we'll now deal with how Gibbs energy of liquid changes as a function of composition. Okay? to deal with that, we can only need to use one statement that we have learned in chapter 4. If liquid and gas are at equilibrium, their chemical potentials should be same, right? As a liquid and also as a vapor, right? Using that simple statement, we can describe the chemical potentials of liquid. Okay? All right. Let's use the whiteboard from here. Sorry. Okay. So we'll treat chemical potential of liquid. So as you see from the slide, quantities relating to pure substances will be denoted with asterisk. Asterisk is this side. So any thermodynamic quantities relating to pure substances will put this side as superscript, right? So for example, chemical potential of pure liquid A, if there is only liquid A, no other substances, we put sign here. Okay? Right. Let's say that we only have liquid A, and A is volatile, so A would evaporate, so forming vapor. Liquid and gas are at equilibrium. Then chemical potential of liquid should be chemical potential of gas. And since there is only A, okay, so we put asterisk, okay, on both sides, okay. And chemical potential of gas can be written as mu A at standard pressure plus RT ln PA star. This is the vapor pressure of A, and we put star here because there is only A, pure substance. Okay? Okay. As you remember, there should be P not here, but to simplify the mathematical expression, we removed it. Okay? If there is, this is for pure A, if there are another substance, A and B, right? And both of them are volatile, so both of them would evaporate, then what will happen? In this case, also liquid and gas phases are equilibrium, we assume it, okay? Then chemical potential of liquid and gas should be same. And let's write that down for component A, okay? So, in this case, chemical potential of A should be same as chemical potential of A in the gas phase, which can be represented using this kind of equation, right? mu A naught plus RT ln PA. Now, since there are additional component B, A is not pure, right? So we did not put star sign here. Okay? Alright? So if you combine these two expressions, you can get mu A is equal to mu A star plus RT log PA over PA star. Okay? Chemical potential of A in a mixture. So this is the chemical potential of A in a mixture. Chemical potential of A as pure form plus RT log vapor pressure, ratio of vapor pressure in a mixture and as pure form. Okay, this is the general expression to describe the chemical potential of liquid. Very important. You have to memorize this expression. Okay? Alright. Let's move on. If I write down the general expression again, mu A, chemical potential of liquid in a mixture is equal to mu A star plus RT ln PA over PA star. Okay? In the next slide, you see there is a Raoult's law. I believe that you have learned this from general chemistry class, right? So, scientists named Raoult did a lot of experiments. He tried to measure vapor pressure of two different, like the mixture of mixing two different materials, which are both volatile. And by experimenting with mixtures of similar liquid with similar chemical structures, this chemist Raoult found that PA is proportional to PA star, and the proportionality constant is XA for similar liquid. By mixing two similar volatile liquids, he found that PA, vapor pressure in a mixture, and vapor pressure is a pure form, they are proportional to each other with constant of mole fraction of A. So which means that this expression can be rearranged as RT ln XA. Simple, right? So some mixture with similar chemical structures follow this law, and this law is called Raoult's law. Okay, and the liquid mixture, basically solution, following this law are called ideal solution. Okay, ideal solution follow this law. Okay, as you see from the slide. Okay. Liquid following this ideal solution or Raoult's law. Okay. If you plot vapor pressure as a function of composition or mole fraction, then you see that they are linear, right? Because vapor pressure is linear to the mole fraction of the material, right? For both component A and B. This is the real experimental data for benzene and methylbenzene. Both of them are very similar in terms of chemical structure. They are linear, right? Vapor pressure as a function of mole fraction. Okay? So these are ideal solutions. Okay? Molecular interpretation of Raoult's law. From Raoult's law, PA is equal to XA PA star, which means that partial vapor pressure of A in a mixture is lower than the vapor pressure of A as pure form, right? Because XA is the value between 0 and 1. The reason is very simple, right? As described here in bold. In a mixture, the presence of a second component hinders molecules from leaving the solution. That's obvious, right? If there is only A, then it can evaporate easily, freely, right? In comparison, if there are other components in a mixture, okay, that will prevent this material, this material to evaporate. So evaporation is less compared to pure form. That's why vapor pressure decreases in a mixture compared to pure form. Okay? We can also interpret it in other words using second law of thermodynamics. Okay? According to the second law of thermodynamics, the entropy law, compared to pure form, in a mixture, there are already more randomness, larger entropy, right? Compared to pure solvent, right? So, molecules would less evaporate. Okay? Alright. Now let's move on. And unfortunately, this Raoult's law is only valid for similar liquid. Mixture with basically having similar chemical structures. For example, for mixture of CS2 and acetone, they do not follow Raoult's law. They follow like this curve, something like that, right? Quite far from Raoult's law. Okay? Instead, Henry, English chemist William Henry, found that for real solutions, especially at low concentration, okay, he found that the vapor pressure in a mixture, especially for solute, you first need to differentiate between solvent and solute. Okay, solvent and solute. If there are two different materials in a mixture, solvent is something which is more. Okay, more amount. And solute is something which is less. Okay, there's a difference between solvent and solute. Okay, so what Henry found is that the vapor pressure of solute in a mixture, especially at low concentration, vapor pressure is proportional to mole fraction, but not to the vapor pressure of pure substance. Instead, they are proportional to some constant, Kb, okay, which is called Henry constant. Okay? And the solution following this equation is called ideal dilute solution. Solution following the Raoult's law is called ideal solution, but following this equation, Henry's law, is ideal dilute solution. Okay? So you need to differentiate between Raoult's law and Henry's law. So let's go back. Let's say for two similar liquids, they are similar to each other. Both of them, A and B, both of them follow this equation, Raoult's law. Okay? And they are called ideal solution. Okay? For real solution, solute at low concentration follow this relation, which is called Henry's law. Okay? So for example, in the case of ideal dilute solution, y-axis is the vapor pressure, P, x-axis is mole fraction of B, solute, okay? At low concentration, when xb is near zero, so this purple line is the real data. When xb is near zero, when concentration is low, okay, they follow this straight line, okay. Vapor pressure is proportional to xb, but with also another constant, which is called Henry's constant, right? And this shows the ideal dilute solution behavior, right? How about when the concentration is high? When xb is near 1. In that case, B is not solute, right? B is solvent, right? Because B is much more than A, right? In that case, when xb is near 1, they follow this line, right? Okay? And this line corresponds to Rao's law, right? Okay? So, if I summarize, for ideal solution, both A and B, solvent, solute, whatever, both of them follow this equation, ideal solution, or Rao's law. Okay? For ideal dilute solution, solute, which is small amount, solute follows Henry's law. On the other hand, solvent follows Rao's law. Okay? That's actually quite obvious, because let's consider ideal dilute solution. Okay? And there are two different materials, red one and blue one. Okay? For blue one, if you compare the situation when these blue ones are in pure form, and in this case, right, there are a few red ones. For blue ones, both situations are not quite different, right? Because there are much more blue ones compared to red ones, right? The environments are pretty much same. Okay? On the other hand, for red one, when they are in pure form, compared to this situation, it's quite different environment. So solute with small amount behaves quite differently from when they were pure form. Okay? That's why for ideal dilute solution, solute and solvent follow different law. Okay? This is experimental data, and you can clearly see that ideal dilute solution case. Alright, so this is the end of section 5.3. Okay, let's move on to section 5.4 and 5. In previous sections, we learned about ideal solution and ideal dilute solution and related to laws, right? Rao's law and Henry's law. Okay. So from the description of ideal solution, we learned actually ideal dilute solution. We saw the effect of solute on the chemical potential of solvent, right? So in these sections, we'll see more about that effect, how solute affect the thermodynamic properties of a solution. Okay, so we'll deal with the properties of solution, especially the effect of solute. Okay. We also consider the thermodynamic properties of liquid mixture. In the previous section, we dealt with gas mixture, right? So we'll also deal with how thermodynamic properties such as Gibbs energy, enthalpy, and entropy change when we mix two different kinds of liquid. Okay, and what are the differences between mixing two different gases and two different liquids. Okay, Furthermore, we'll learn about colligative properties, which is representative examples of the effect of solute on the solution. So you might be familiar with boiling point elevation, freezing point depression, or osmosis. Okay? So we'll deal with this. And after that, we'll also consider the behavior of real solution, not ideal or ideal dilute solution. Okay? Okay. Liquid mixtures. As we did in previous sections, we'll see how different thermodynamic properties change upon mixing two different liquids. Okay? So we will calculate first the Gibbs energy of mixing for two liquids. Okay? We can do the same procedures to calculate it. We first calculate the initial Gibbs energy before mixing two different liquids and after mixing. Okay? Here, we assume that the liquids, two different liquids, form ideal solution. Okay? We just assume it. So, before mixing, let's say that we have two different liquids, A and B. Okay? Before mixing, the Gibbs energy is Na mu A plus Nb mu B. Here, we put star here because they are not mixed together yet, right? So they are in pure state. Okay? And we'll calculate the Gibbs energy after mixing. Gf here. Okay? After mixing, it becomes solution, right? Mixture of A and B. And we learned that for ideal solution, chemical potential of a solution, especially for solvent or solid, for ideal solution, chemical potential after mixing is equal to chemical potential in pure form plus RT log mole fraction, right? Remember? From Raoult's law. Okay? So you put this in here, okay? Because Gibbs energy after mixing would be Na mu A plus Nb mu B, right? And mu A here should be mu A star plus RT ln XA. Mu B should be mu B star plus RT ln XB. Okay? So, simply we can calculate Gibbs energy of mixing by subtracting Gi from Gf. So, delta mix G should be equal to nRT XA ln XA plus XB ln XB, which is same as Gibbs energy of mixing for two different gases, right? Since Gibbs energy of mixing is same, Gibbs energy of entropy is also same, right? Minus NR XA ln XA plus XB ln XB. So as you see, Gibbs energy mixing for two different liquids is negative. So mixing process is spontaneous, right? And Gibbs energy of entropy of mixing is positive, right? And also enthalpy of mixing is 0. So similarly to mixing two different gases, mixing two different liquids, especially to form ideal solution, has same Gibbs energy of mixing, entropy of mixing, and enthalpy of mixing. Okay? So the driving force to mix, to make the mixing occur spontaneously is entropy change, entropy increase, right? It seems that mixing two different gases and mixing two different liquids are same, but it is quite different, right? The main difference is that for mixing two different perfect gases, basically perfect gas have no molecular interactions, right? No molecular interactions whatsoever. But liquid molecules have molecular interactions. Okay? But if the solutions are ideal solution, you remember what ideal solutions are, right? Ideal solutions are solutions with similar chemical structure. Okay? So since they have similar chemical structures, their average interactions between A and A, or B and B, or A and B are quite similar. The interactions are similar. There are interactions, but interactions are similar. So that's why we got the same thermodynamic properties upon mixing two different liquids as mixing two different gases. Okay? And you have to note that for real solutions, not ideal solutions, these interactions between A and B, or B to B and B should be totally different, right? So the thermodynamic behavior of real solution will be quite different from those of ideal solutions. Okay. In these cases, we only considered the case in which when two different molecules mix together completely. Okay? But sometimes molecules of one type might cluster together, which means that if you mix two different liquids, they do not mix together. For example, water and oil, right? Everybody knows that. Oil and water do not mix together, right? Okay. In that case, mixing is not spontaneous. Instead, separation of two different liquids is spontaneous. Okay? And these kind of liquids that do not mix together are called immiscible. Okay? Right? So for immiscible liquid, there could be any reasons. For example, which means the fact that two liquids are immiscible means that separation is spontaneous, or mixing is non-spontaneous, right? Means that mixing has positive Gibbs energy, right, instead of negative, right? And positive Gibbs energy could be due to either positive enthalpy change or negative entropy change. Okay? So there are miscible ones, immiscible ones, and also there are partially miscible liquids. Partially miscible liquids are some things that they mix sometimes, but in other conditions they do not mix. Okay? So there are three different kinds of miscibility when you deal with a mixture of liquids. Okay? Real solutions and excess functions. Okay. As we have heard, real solutions are quite different from ideal solutions because they have molecular interactions, especially different molecular interactions between A and B, and B and B. Okay? So to describe those differences between real solution and ideal solution, okay, we introduced a new physical variable called excess function, or XE. Okay? X superscript E. So for example, excess entropy, SE, is defined as the entropy of mixing of real solution minus entropy of mixing for ideal solution. Basically, difference between real solution and ideal solution. That's the definition of excess function. Okay? And real solutions would be very complicated, right? As we encountered dealing with real gases, right? So, as we used van der Waals equation as a model to describe the behavior of real gases. Here, we also introduce a model system to describe the behavior of real solution, which is regular solution. So regular solution is a model for real solution, which has properties of excess enthalpy is non-zero. There is excess enthalpy, but excess entropy is zero. So regular solution, a model system, has these properties. Okay? Which means that since excess entropy is zero, that two different molecules, two different liquids mixed together randomly, right? Because this one is zero, it means that this and this are same, okay? But since excess enthalpy is not zero, meaning that they have different molecular interactions between different kinds of materials, right? Okay. So for example, here shows the behavior of the real solutions, or actually regular solutions. So for example, figure A is a mixture of benzene and cyclohexane. As you see, as a function of composition, excess enthalpy has a certain number, right? Not zero. For example, this one, B, is a mixture of tetrachloroethane and cyclohexane. As you see, as a function of composition, the y-axis is excess volume. Volume also changes, right? So similarly, we can deal with other thermodynamic properties using this definition of regular solution. Oops. Sorry. There is a regular solution. Sorry about that. So, regular solution is a model system to describe the behavior of real solution. Okay. So, to express this concept, basically the definition of a regular solution, where excess enthalpy is non-zero and excess entropy is zero. Okay. Excess enthalpy is defined as this. Okay? There are a lot of weird variables, right? Number of moles, psi, which is a constant representing the molecular interactions between two different molecules, right? RT, XA, and XB, mole fractions. Okay? So we simply assume that Xe has this form. Okay? So it depends, the excess enthalpy depends on the number of moles, right? Basically the composition. And also it depends on molecular interactions, right? Okay? So for example, if this psi has positive number, then excess enthalpy is positive, like this. Okay? If psi is constant, is negative, excess enthalpy is negative. Okay? So depending on the sign of this constant, you'll have different sign of excess enthalpy. Okay? So, based on the definition of excess enthalpy, you can simply get the expression for Gibbs-Ellerson mixing, right? Up to here is the Gibbs-Ellerson mixing for ideal solution. Okay. Now, since there is enthalpy term, for ideal solution there was no enthalpy of mixing, right? Since there is now enthalpy term for regular solution, you need to add this term here, right? And Gibbs energy of mixing for regular solution looks like this. Okay? And interesting thing is, if you plot Gibbs energy of mixing for regular solution as a function of composition, you see very interesting diagram, right? These numbers shows this constant psi. If psi is low, has low number, Gibbs energy of mixing looks like this, same as normal solution, like ideal solution. But when psi is larger than 2, there are minima here, 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 and here. Okay? Which means that this composition and this composition have lowest Gibbs energy of mixing. So, lowest Gibbs energy means the process tends toward this position, this composition spontaneously. Okay? Which means that when this constant is large enough, over 2, this regular solution separates spontaneously into 2 different compositions, 2 different phases. Okay? So regular solution shows very interesting behavior and is an example of real solution behavior. That's why regular solution is very good model to describe real solutions. We'll get back to this point again, how this separation, like spontaneous separation, occurs for real solution. Okay, let's move on. Colligative properties. So colligative properties, the meaning is properties which depends only on the collection of particles, which means that colligative properties only depends on the number of moles of material, not the kinds. Okay? Only depends how much material, especially how much solute are present in the solution. It does not depend on the kinds of materials. Okay? So examples of colligative properties are boiling point elevation, freezing point depression, and osmotic pressure. Actually, solubility of liquids and solid are not colligative properties. Okay? Because, for example, we know that if you dissolve salt in water and if you dissolve sugar in water, the solubilities are totally different, right? Solubility depends on the kinds of materials. Okay? The reason why we put solubility here is that the process dealing with the solubility of liquids and solid in solvent is same as the way we deal with these other colligative properties. Okay? So there are 3 colligative properties, right? Boiling point elevation, freezing point depression, and osmotic pressure. Okay? And each of these properties only depend on the composition of mixture, how much material are present in the solution. Okay? And to deal with colligative properties, there are important assumptions. Okay? I show here. The first assumption is that for the solution has solvent and solute, right? To describe colligative properties, solute is not volatile. Only solvent is volatile. Okay? When we dealt with ideal solutions or other types of solutions, we assume that both solvent and solute are volatile. But here, describing the colligative properties, solute is not volatile. Okay? That's one important assumption. Another assumption is that similar, solute does not dissolve in solid solvent. Okay? You have solution. Comprising solvent and solute. If you decrease the temperature, solution will freeze, right? And when it freezes as solid, we assume that solute does not dissolve in solid solvent. Only solvent freezes as solid. Okay? These are two assumptions dealing with colligative properties. So, let's start. What would happen if you put non-volatile solute? We already have seen it. We have pure solvent. Okay. Pure solvent has chemical potential, okay, mu A star when it's pure. We put some solute which is non-volatile. Okay. As you put other materials, the chemical potential of solvent decreases, right? Because it follows this equation. Okay. Mu A for the solute solution is mu A star plus RT ln XA, right? Okay. Okay. So, okay. So compared to pure solvent, solution, especially for solvent, has lower chemical potential compared to pure form, because if we assume that this solution forms ideal dilute solution, solvent should follow this formula, right? Mu A should be equal to mu A star plus RT ln XA. And XA is smaller than 1, okay? Since this is mole fraction, so this part is negative. Okay, so chemical potential of solvent in a solution is lower than the chemical potential in pure form. Okay, so this lowering chemical potential is the main reason why we observe colligative properties. Let's see why. Okay, why we experience boiling point elevation or freezing point depression. Okay. Have you seen this diagram before, right? Okay. Chemical potential as a function of temperature. Okay. At low temperature, solid has the lowest chemical potential. In the medium, liquid has the lowest chemical potential, vapor following. Okay. Let's say that as pure form, as pure state of a certain material, they have this chemical potential: solid, liquid, as this blue line, and vapor. Okay. And if you put some solute, non-volatile materials into this solvent, okay, chemical potential of liquid lowered, right? As we have seen here, okay? Chemical potential of liquid decreases if you put some solute into a solvent, okay? Then, let's see what happens. Originally, the melting point is at which chemical potential of solid and chemical potential of liquid meets here. Now, melting point decreased to here, right? Okay. Upon adding some solute into a solvent, melting point decreased, right? How about boiling point? Originally, boiling point was here, at which chemical potential of liquid and vapor meets here. Now, after mixing, after putting some solute into a solvent, chemical potential changes here. Right? Boiling point from here to here, boiling point increased. Okay? Simply, we added some solute into a solvent, and we are experiencing depression of freezing point, and elevation of boiling point. Okay? Simple, right? You can understand also qualitatively why boiling point increases. For example, let's see this diagram. Let's say that first we only have one material, pure form. Pure material A solvent has vapor pressure of PA star, right? If you put some material in it, okay, as you have learned before, vapor pressure decreases because these other materials hinders these original solvent molecules from vaporizing, okay? So vapor pressure is lower. So to make this material boil, okay, we need to heat more. The temperature will be higher. Basically, boiling temperature will be higher for this solution compared to pure form. Okay, that's why we are experiencing boiling point elevation when you add solute. Okay. Then, how much elevation and how much depression we experience upon adding solute? Alright, let's calculate it. The calculation is simple, actually. When you add, we have solvent A, and A is the only volatile material. So in the gas phase, we also have only A, and we add some B solute in the liquid, okay? And equilibrium between liquid and gas occurs at some temperature, right? And at equilibrium, we know that chemical potentials of two different phases are same. Okay? So chemical potential of A in the gas phase should be same as chemical potential of A in the liquid phase. Okay? So chemical potential of A in the gas phase, here we put star because there is only A in the gas phase, right? B is not volatile. That was the assumption in dealing with colligative properties. Should be same as chemical potential of liquid A in the solution, which should be equal to this, right? For ideal diluted solution, mu A star L plus RT ln XA. And from this simple statement, we can derive how much temperature elevation we experience. So let's do the derivation. Sorry. Okay. Alright, so you have mu A star G is equal to mu A star L plus RT ln XA. Okay. You start from here. Okay. If you rearrange it as a function of ln XA, then you have RT mu A star G minus mu A star L. Okay. Gives a chemical potential of A in a pure form in the gas phase, chemical potential of A in the pure form in the liquid phase. Basically, change a difference of molar Gibbs energy, right? Because chemical potential is same as molar Gibbs energy as a pure substance, right? So this is basically molar Gibbs energy change upon liquid to gas vaporization. Okay? what we do here is that we differentiate both sides with temperature. We basically differentiate both sides temperature dt. Then what we get here is that this expression is basically delta vaporization Gm over T, right? If you recall, if you take the derivative as a function of temperature for Gibbs energy over T, which was Gibbs-Helmholtz equation. Okay? If you take the derivative of this is just constant, what you get is minus T squared delta H. Okay, remember? Okay. You can check Gibbs-Helmholtz equation. Okay. Now, let's do the integration. Okay. So, let's move dt to this side. Okay. So move dt to this side. Okay. And let's do the integration. So here we do integration for ln xa, okay, from pure state to solution, right? When it is pure, xa is equal to 1. If it is 1, ln xa is 0, right? And after adding some salt, basically solute, the result is ln xa. For this, as a pure form, the temperature is boiling temperature of pure A, right, to the final boiling temperature. Okay? Let's see. Alright. So if you do the derivation, the integration, what you get is the left side is ln xa. Okay. Right side, what you get is delta vaporization Hm over R 1 over T minus 1 over T star. Okay. And ln xa is equal to ln 1 minus xb, right? Okay. And if xb is really small, okay, if solute is added very small amount, and then 1 plus something is approximately same as minus xb, you remember? Okay. Okay. When plus x is about x, when x is very small. Okay. So if you rearrange it as a function of xb, it's equal to delta vaporization enthalpy R okay. So here if you rearrange it, T star T over T minus T star, okay, and T minus T star is the thing that we want to calculate, right? Delta T, how much temperature increases, okay, how much boiling point increases, and you might remember that temperature increase upon adding solute is relatively small. So T star and T is very close to each other. Okay? So approximately T star times T is equal to T star squared. Okay? So if you rearrange it, you can get that delta T is equal to RT star square over delta vaporization mxv kxv. K is a constant here, okay? As you see from the slide. Okay. All right. So you can do the derivation by yourself. Okay. And finally we get this. Okay. You got the result here. So what you got is that delta T, boiling point elevation, only depends on XB, mole fraction of solute, how much materials are added. Okay? This constant K comprise gas constant, boiling point, and the enthalpy change upon vaporization. Okay? It's basically constant for a specific material, right? Okay. And usually, instead of using mole fraction, people usually use concentration, such as molality. So we can change this same expression by replacing xb by b, molality. Then also the constant will be changed, right? So for this expression, we call k sub b as boiling point constant. Okay. Right? Can you follow? Okay. We can do the same thing for the freezing point depression. Okay. We have liquid A. Okay. We have solute B, and we decrease the temperature. Then we will have solid A. As you remember, one important assumption dealing with colligative properties was that A is the only solid, right? B does not freeze as solid solvent, right? Okay. So here A plus B, here A. And at equilibrium, chemical potential should be same. Okay. Chemical potential of liquid A should be same as chemical potential of solid as a pure form. Okay. So you have this expression, basically same expression as we got for boiling point elevation, right? So we'll get the same result actually, right? Delta T. Freezing point depression is some constant times xb, okay? Here that constant is equal to this, right? Our melting point, melting temperature, and delta H for fusion, okay? Similarly, xb can be replaced by concentration, molality, okay? Alright. Solubility. I mentioned before that solubility is not colligative property. Then why? Why do we consider this, okay, in this section? Let's say that we dissolve some solute in the liquid. Okay? Then that solute, the solid, dissolves until the solution is saturated. Okay? So let's say that A is solvent and B is solute, solute, and we dissolve it until it is saturated. Okay? Then, after saturation, the remaining solute B will be precipitated as solid, right? So there will be two different phases. One of them is A saturated with B, okay, and B as solid. And at some temperature, these two phases would be in equilibrium. Okay? At equilibrium, chemical potential should be same for B, right? Here, chemical potential of B as solid. Okay? Chemical potential of D as in the solution. Okay? They should be same. Okay? Since this is same, we get this expression. Same as we got for boiling point elevation or freezing point depression. Okay? And as you see, this expression is basically same as this. So using same mathematical derivation process, we can get information about solubility. Okay? That's why we just introduce solubility here, although it is not colligative property, because we can use same formula to get information about solubility. So we get basically same result. But the problem is, to use this equation, we assume that the solution is basically ideal, right? But real solution is not ideal, right? So solubility is not colligative property. I mean, you can easily imagine that. Okay, there is total big difference between solubility of salt or sugar in water, right? So we know that it's not colligative property. Last one. The last colligative property is osmosis or osmotic pressure. Okay. All right. Let's say that we have two different solutions here. One of them is pure solvent here on the left side. On the right side is solution. Solvent added by, solvent with some solute. Okay. And let's say that we have some membrane between these two solutions, which is semi-permeable membrane. Okay. This semi-permeable membrane has properties of they are permeable to solvent but not to solute. Only solvent molecules can go through this membrane. Okay? Then, in this situation, on the left side there's only pure solvent. On the right side there is solution. Then, if there is semi-permeable membrane, these solvent molecules would penetrate to the right? Because this one has higher concentration compared to pure solvent, right? Okay? In this case, osmotic pressure is defined. Osmotic pressure, denoted as Greek letter pi, is defined as the pressure that must be applied to stop the influx of solvent. Okay? In this situation, these solvent molecules will try to move to the right. To stop it, we need to exert some more pressure to the solution here, to this side, to prevent the solvent from coming to the right. Okay? That pressure is called osmotic pressure. Okay? And osmotic pressure is also a colligative property. If you just see the result, osmotic pressure pi is equal to very simple form. BRT, molar concentration of solute RT. It's very simple. Only depends on the concentration of solute, not the kinds of solute, right? So this equation is called Van Hoff equation. Okay. So let's derive why osmotic pressure has this simple form. Okay. Let's do the derivation. Okay. Osmotic pressure. We'll derive that y pi is equal to b RT. So if you recall the diagram, semi-permeable membrane here between two solution. Okay. So if you apply osmotic pressure to the solution on the right, okay, here osmotic pressure pi to the right, these two solutions would be in equilibrium at some point, right? And at equilibrium, chemical potential should be same, okay? Right? And the pressure exerted on each of these solutions would be here. For here, there will be some pressure from the atmosphere, P. Here, the pressure will be atmosphere pressure plus osmotic pressure to make this solution in equilibrium, right? Alright. So, at equilibrium, chemical potential should be the same. So, chemical potential of solvent A on this side would be mu A star at pressure P. Okay? Since there is only pure solvent on the left side, we put star on the left side. Okay? Right? How about on the right side? The solution. Okay? Solution of for the solution, chemical potential of A will be mu A, but the pressure applied in this solution will be P plus pi. Okay? So these two should be same. Alright. Okay. And we know that for the solution, the chemical potential can be expressed as mu A star plus RT ln XA. Remember? Okay. Chemical potential of solution is chemical potential of pure solvent plus RT ln XA. Simple, right? Another important thing is chemical potential, same chemical potential of pure solvent, but at different pressure. Okay? Let's put it here. Pi. Okay. We know that how chemical potential changes as a function of pressure. Remember? Okay? How much? Like, what was that? At constant temperature was molar volume. Remember? So this should be equal to mu A at P plus integral Vm from P to P plus pi. Okay? How chemical potential or molar Gibbs energy changes as a function of pressure was molar volume, right? So this is equal to this, which corresponds to mu A P plus Vm pi, because molar volume of liquid is basically constant. Okay. So if you put this here, what you get is very simple actually. 0 is equal to Vm pi plus RT ln XA. Okay, let's write it as a function of pi. Pi is Vm over RT ln XA. This is minus. Okay, and ln XA is ln 1 minus XB. Okay, and as you did for the derivation of boiling point elevation, 1 minus ln 1 minus XB is approximately minus xb. Okay? So what you get is xb over vm rt. Okay? And xb, mole fraction of b, is defined as nb over na plus nb, right? Okay. If we add small amount of solute, nb will be much smaller than na, right? So it's approximately nb over na. Okay. So if you put that here, what you get is nb over na times vm rt. Okay. And na times v is number of moles times molar volume is volume. Okay. Number of moles over volume is molar concentration. Okay. So finally we get pi is equal to BRT. Okay. Osmotic pressure only depends on the concentration of solute in a solution. Only concentration, how much materials are in it. Okay. And osmotic pressure can easily be measured, and by measuring osmotic pressure we can determine the concentration of solute, and if you know the concentration you can have information about molecular weight about this solute. Okay, if you know the volume, right? So measuring osmotic pressure is one simple way to determine the molecular weight of an unknown solute in a solution. Alright, so this is the end of section 5.5.